Hello folks, so in this video we're going to talk about how we can use a system to model a situation. So here's our situation today. We have two cars. One car is cheaper at $11,000 and costs 22 cents per mile to drive. So that's kind of taken into account like maintenance and gas and all that stuff. And car B is a little bit more expensive, costs $11,300, but is a little more fuel efficient, so only costs 20 cents per mile. So step one, it's a random equation for both of them. So, and this is where our function notation is going to come in, because I can rewrite this and be able to keep the equations in check. So I'm going to say let f of, I think the book wants us to use d, so d stands for distance, equal the total cost. So this would be the dependent variable. Total cost definitely depends on the distance you drive. So the total cost of car A after driving for D, I think it said miles. Okay, and it makes sense for miles because our units for our gas mileage or our cost per mile is again per mile, so it makes sense to measure D, the distance, in miles. Likewise, we're going to let G of D equal the same thing, the total cost, but except for car B after driving. There's these little dash lines. I don't use it often, but that just means copy what we saw above downward. Okay, and the last part is we have to actually define what D is. So D again is the distance driven in that car. Distance driven, again in miles. Miles. Alrighty, so I'm going to need a little bit more space here. Hang on. Alrighty, so I've given us more space. And so let's actually come up with the equations. So that purchase cost, remember that purchase cost means you haven't actually driven it yet. You just bought it. And so that would be our y-intercept for our line. And then that would mean that our 22 cents per mile is our slope, or our rate of change, right? Our slope. I think that we do have to mention here, and that I actually forgot, is we did not give our units for our costs. Since we're using $11,000 and $11,300, I think it makes sense for our total cost to be in dollars there. Okay, so that would mean that for f of D would be $11,000. So I'm going to write it like so, 11,000 first. Now usually you put your slope first, but I'll just put our y-intercept first. It doesn't actually matter because addition is commutative. And then plus, well, for each mile, so that's D, again, that is our x, our independent variable. How much does it cost to drive? Well, it costs 22 cents. So 22 cents per mile actually means $0.22 per mile. Oh, sorry, you can't see that. $0.22 per mile. And so in this case, for f, our equation should say 0.22 D. And likewise, G of D should be 11,300 plus 0.20 D. And those would be our equations. Now, it didn't ask us to do this, but we could also draw a graph to see what's happening here. So I'll draw a rough sketch here. Let's pretend that this first part right here is 11,000. So this is, again, the total cost in dollars. This is miles driven. So make sure you can see this. So the first one, and I'm going to draw F right here. It looks like maybe so. Now, it wouldn't make sense to extend this line backwards because you can't drive at negative miles. So the domain of this situation should be miles from 0 to positive infinity. Okay, now I'll draw the second line here in blue. So this, again, this is F of D. And the one in blue here, again, it costs a little bit more. It costs a little bit more, but the per mile cost is cheaper. So that's why its slope is less. So we do know that at some point you're getting, excuse me, the total cost of the more fuel efficient car B and car A at some point is going to be the same total cost. But after that, then eventually the blue one, G, car B rather, is going to be better value in the long run, because eventually you're gonna pay for that $300 kind of bonus, or yeah, I guess bonus would be the right word. You're gonna have paid for that in the extra gas mileage, or in the extra cost per mile. So yeah, if you're only driving it for a little bit, then the cheaper car is the one to go with. But if you're gonna keep it for years and years and years, you're gonna want to buy the more expensive one at first. All right. So what exactly then do G of 1,000 and F of 10,000 tell us? So the nice thing about this is that because we've labeled them F and G, we know exactly what this says. So F, remember, we can kind of just plug this in right here. F is the total cost of car A after you've driven it for, now this says 10,000 miles. And so I could actually evaluate that. F of 10,000. So F of 10,000 is equal to 11,000 plus 0.22 times 10,000. Or sorry, 10,000. We need an extra zero in there. And then likewise, G of 1,000 says that, well, I'll just plug in 1,000 here, plus 0.20 times 1,000. I'm going to kind of take a second here and use pull up my handy dandy calculator, but I think this should be, let's see, that would be, all right, I pulled out my calculator because my brain was frozen there, and it's F of 10,000 is 13,200. G of 1,000 is 11,500. And so think back to what this means. This tells us that, hey, F was telling us about the total cost. So after 10,000 miles, or having driven it for 10,000 miles, car A, or car A's total cost will be $13,200. And likewise for car in G of 1,000, G of 1,000 tells us car B is going to cost 11,500 after we've driven it for 1,000 miles. Right? The last part here is how far will we have to drive before we can say, or this should actually say car B. Car B has the better value. And again, what this means is, again, if we look back at the graph, from starting up till here, F of D is smaller, right? The outputs are smaller than G. Right? The Y values are below. Remember, these just mean the Y values, meaning that car A is cheaper. But after that, so at this point specifically, they're the same cost, the exact same, right? Same miles driven, same cost, same cost. And then from here onward, then actually G of D is less than F of D, which means that car B is cheaper, assuming that you've driven it for this long. So the question is, when does this happen? Well, if that's the case, we have to figure out when do cars A and B cost the same amount. And when we say cost, we mean like the total cost. Well, if that's the case, then that really just means the same amount that would mean that f of d is equal to g of d. And now we can use our equal values method or substitution method to actually solve the system. So f is 11,000 plus 0.22 d, g 11,300 plus 0.2 d, or 20. You don't have to put the 20. I just put the 0.20 because it's money, so we always kind of round it off to 2 decimal places. Okay, well, we're going to want to solve this one, so I'll subtract from both sides. So I'll subtract the 11,000 over here, subtract the 0.2 d on the left side, and I'll get 0.02 d equals 300. Divide everything by 0.02. Let's see, I'm going to have to move my decimal point over here. So 30,000 divided by 2. D is actually equal to 15,000. So what does this mean? So remember, D, this is in miles. Let's not forget that. So this means that after driving both cars for 15,000 miles, the cars cost the same amount. The cars' total cost is the same. However, from then on, so from that point on, we would say then actually car B is cheaper. So if we were actually kind of asking the question, we could give it as an interval, or sorry, as an inequality, or the distance driven. Again, we're answering the question now, how far do you have to drive it? Well, you have to drive it at 15,000, it costs the exact same. So for B to actually be cheaper, the distance driven has to be more than 15,000 miles. So hopefully this made some amount of sense, and you can see how we can use systems and also function notation to make our lives a little bit easier.